a summary of all those nice numbers that we put in the report. We put in the report the different crops. We had the different centers reporting from different regions. And you can see in the y-axis the rate of genetic gain that was reported for the different crops, regions, and centers. And we were kind of, expecting most of the numbers in this region between 0 and 2%, and that was the case. So that was a good check. We also found some big numbers, some low numbers. You might remember those. Those are your numbers. Like I said, we are here just to share, your stuff. We're not making up anything. But we kind of figured out why these numbers were so big. So that's kind of the learnings that we want to share also today. But it was actually curious that almost nobody actually reported negative genetic gains. I think there was only wheat was there. So that kind of brings us to the idea that this exercise was not about the numbers, right? It was mostly about being aligned, showing that we can standardize. So you don't have to worry about being honest if something doesn't look, that good. This was not going to be used against you. Okay, so why we need key performance indicators, Elisa? So we were talking about the breeding process, and that we have all these market segments, product profiles, and then breeding pipelines attending them. And well, basically you can come up with different numbers to assess how good you are doing in the different activities. You can maybe come up with a number to assess that maybe the number of plots that your technician is, basically putting in the field. That could be a KPI. Or maybe you can say, okay, what is the number of genotypes that are, that the crosses that are real crosses? Maybe you did like 100, and then you actually check with markers, and maybe 80% are real crosses, the 20% are not real crosses, or basically maybe some cells or some confusion on the genotypes. That can be a KPI. You can say, okay, I'm going to monitor how good my technician is doing the crosses with that particular number of real crosses. Basically, there can be KPIs in all the different parts of the breeding process. But the reason why realized genetic gain was picked as the first KPI to show to the donors was because it really kind of shows the entire performance of the breeding program, right? Like all the activities. Because maybe the quality check is a good KPI, but it only allows you to show the performance of your technician. And in this case, the realized genetic gain allows you to see the performance of the entire breeding program. So that's kind of the reason why was the realized genetic gain picked. And we want to adopt KPIs. I think this has been a message that has been clear for a long time, because the CG wants to become a data-driven institution that takes decisions based on numbers that are informed by data that can take us in the right direction. So there is different steps, in moving to a data-driven institution. Of course, we can start with just ignoring the data. We just trust our gut feeling, and that's how we take decisions. Or, maybe we have some data, but we don't use it that much. We're a bit indifferent. Maybe we know that exists, and we might use it for basing some decisions, but not big ones. Or maybe you start to really use it in the decision-making process. Like I said, there could be many KPIs. And actually, like I said, we are just here to support your ambitions, because you are the ones that really decide the KPIs. There can be, for example, in some institutions, maybe royalties is a thing. Maybe, the accuracy in your trials, the heritabilities, the cycle time, the number of introgressions, number of QTLs mapped. There can be several KPIs. So you may want to think on, what are the next round of KPIs that you want to work with. So I'm going to try to, to go chronologically. So when we started and we were, given the responsibility of come up with some guidelines. So I'm going to start with that process, how we develop those guidelines, and then how we got into the real analysis. So when we were just asked, okay, let's get and calculate genetic gain across the CG, you actually provided several questions in that moment. Hey, but should we use historical or era trials? What methods should we use? What stage of evaluation should we use for the calculation? How many checks? Should we use blues or blobs? How many trials, et cetera, et cetera. And many of you contributed to answering these questions. So, but before we actually started simulating, we wanted to see what was in the current literature, right? I mean, what was at least the current understanding on how to calculate genetic gain. So there was actually some nice papers, some good reviews, especially on the animal breeding side. There was quite a lot. In plant breeding, there was several good analyses even already done by the CG programs in the past. But you know, some of the reviews, one that was interesting was one that was talking about the methods to estimate genetic gain. And some of the methods, you know, was kind of difficult to follow because they say things like this: control population, EBB, variety trial, error trial, phenotype. But if you started, you know, to think a bit more about the topic, we started to realize that these were not actual methods. These were different variables that can affect the estimation of realized genetic gain. For example, when they were talking about control population, this was a way to connect the data, to look at connectivity. EBB was mostly referring to a method, to an actual, you know, statistical method to calculate genetic gain. When they say variety trial, they were referring to the stage of material that was being used for the calculation. Error trial, they were also, you know, referring kind of to the connectivity or the source of the information. And when they say phenotype, they were actually referring to a statistical method. So there was many things, you know, in these reviews kind of, you know, mixed, that it was difficult to just translate into practical guidelines for you. So we started to address question by questions. So one of the first questions was, okay, should we use the historical or error trial information that we have? And by default, we knew that there was pros and cons to each source of data. For the case of the historical trials, we knew that the connectivity was not going to be as good, you know, talking about connectivity across years, was not going to be as good as the error trials, because in the error trials, it was built in that you take materials from the different years, you put it in the same trial, connectivity is complete, right? I mean, there is no problem there. But if you were going to take historical trials, basically some genotypes showing up in year 1 were not going to show up in year 5 or in year 6. So there was less connectivity depending on the structure of the experiments. But there was also, of course, some pros of using the historical trials. There was going to be better TPE coverage because this extended over several years, many places, whereas in the case of the error trials, you were mostly running those trials for 1 year, maybe 2 years, 1, 2 locations. So there was also a weakness there. So depending, of course, on how did you structure your data sets, we wanted to understand, okay, is it a good idea to use historical trials? Because your concern was error trials might be expensive. We cannot run this every year. So we ran a couple of simulations, and actually, to our surprise, it looked pretty good. It looked like actually error trials, as expected, they were good to capture the true genetic gain. Because these were simulations, we knew the true genetic gain. We could put, you know, all the error that you want on the environment, on the years, et cetera, et cetera. But the whole point is that it was that we know the true genetic gain, and we were trying to estimate it, and the error trials were really good for actually estimating the true genetic gain because the connectivity was full for you know, considerable levels of G by E and G by Y, let's say. Yes?
What is an error trial for?
Ah, okay. Then let me take a step back. So the error trial is a specific type of trial where you want to, that you design for measuring the genetic gain. So you go to your germplasm, let's say you go to your germplasm bank where maybe you have been storing, you know, some of your germplasm from the different years from your history, and then you can take a sample, let's say from your stage 1 of evaluation or your stage 3 of evaluation. You take from multiple years, then you bring them together to the field, you grow them, and then you can measure if there was progress or not, because you are representing the entire history of the breeding program.
Is this the best variant of each cycle of recombination?
Well, actually, it's up to you. That's one of the things that we're going to discuss. But normally, you pick a single stage. Let's say the best stage, where the best germplasm is, maybe where the best 10 entries are. the very late stage of evaluation. So you take the best 10 entries from year 1, the best 10 entries from year 2, year 3, year 4, year 5. So you can create that regression where in the x-axis you have the years of origin or years of release. And then in the y-axis, basically you put the performance of the material. And if you see a positive trend, that means that your germplasm has been improving for that particular trait. If you don't see any trend, okay, then that was not a trait that was maybe being improved. Boja, I think you wanted to say something.
The same question.
Ah, okay. So that is...
One or just sampling or how to take those?
Exactly. Sampling germplasm from a given stage, from the entire history of the breeding program, or a specific period of the breeding program. Last 5 years, last 10 years, last 20 years. That's what the people call era trial. So running a trial that is showing the different eras of the breeding program. So you capture that information, you analyze it, and you can estimate the genetic gain. So we were running several simulations, and always, for example, this is one dot here, for example, represents one of these pictures where we calculate or estimate the genetic gain. We have the true one. Remember that the genetic gain is actually the slope. So it doesn't matter the intercept, because the intercept is actually difficult to really know. But the genetic gain is actually the slope. So you can see that the slope is very close for the different simulations. Like I said, this one, imagine that the slope is, I don't know, 0.2. And here, when you estimate it, it's 0.21. So it's very close to the true one. So this is what it's representing. For example, here, is saying, okay, the simulated genetic gain for being the true one is 0.12, and the estimated was 0.09. And over several rounds of simulation, you can see how effective the era trial method can be for estimating genetic gain. For historical trials, something that we didn't foresee in that moment, and that's, in that moment, it looked also terrific. Oh, it's also as good as data trials. Let's go for historical trial information. When I say historical trial, it's just going back to your database, extracting the data, analyzing it, removing some noise, year, spatial, environmental effects, and again, plotting the year of origin of the material, checking the performance by the performance, and then calculating the trend. Well, it turned out that in that moment, it looked terrific. We said, our recommendation is to use historical trial information. Go for it. What we didn't foresee is that in our simulations, we were basically simulating very good patterns of connectivity. Basically, checks stay in there for long periods of time. As we will see later, when we take a look at the real data, we will notice that there was some discrepancies. But in general, both methods can be really good to estimate genetic gain, but the historical trial is a cheaper one. That was kind of the first question that we addressed. Then the next question was, okay, but what stage of germplasm we should use for running this analysis? Because we have early variety trials, late variety trials, and we go over and over and over until we have very few entries that are basically being tested on farmers' fields. So again, we knew that there was pros and cons before starting to simulate. Just by default, we knew that in the case of the early testing, the early trials, the entries that are planted there normally are present in very few locations. So they don't cover the TPE that much. That's what we're trying to represent here. For example, they don't cover the TPE that much. But in the case of the connectivity, there's also, kind of limited compared to our trials. But as you move, later and later stages, we know that they start to cover better and better the TPE. Suddenly, we have seen some of your data sets being in 40 locations, 30 locations, 20 locations, very robust TPE coverage. And we said, okay, well, there seems to be some pros in the TPE coverage. But then what actually, happened in the simulation was more something like this, that there was really no difference depending on the stage. So for example, if you were picking an early stage trial, and remember, we're talking about historical trial data sets because that was the recommendation. If you were to extract from your database the early trials and get the genetic gain, or if you were taking, let's say, the stage 2 or intermediate trials and calculating genetic gain, or taking the late stage trials in calculating genetic gain. In the simulation, it turned out that there was just more or less dots because there was more or less entries, but the slope was the same. The only thing that was different was the intercept, because we know that the performance of the late stage trials, in general, they have better performance than the early trials, but in essence, across several simulations, really the slopes was the same. I mean, there was no difference because it's the representation of the same program. So somehow you're saying, okay, this program has this rate of gain independently of the stage. The stage will just tell you a different intercept. So that's also something that was interesting. So the recommendation in that moment, again, and I'm looking at Bert because he was one of the ones that combined several stages and really look at this with real data. The recommendation in that moment was pick the stage that you want. There's no problem.
But you have to pick the same stage across all the years, right? If you want, or like maybe, in 2010, maybe I can pick stage 1, and then 2020, if I pick stage 3 lines, is that the same? Or
yeah, you could say the same period of time. Let's say 2010 to 2020. Okay. And then in 2020, there is some stage 1, and in 2021, there is some stage 1. I mean, it's not going to be exactly the same entries because as you are noticing, some of this material, maybe stage 1 is not going to become stage 2 until the next one. So if you take a stage 2, you're taking some previous material that if you were taking a stage 1s. So of course, there is, but in essence, again, we are in the time of the simulations. We're simulating a program that is becoming, is working steadily. It has all the stages, it has all the cohorts, it has all the complexity, but it's assuming at this point that it's well connected and that basically, when you see at the results, there was no difference for the same period of time because it's steady, so the slope is the same. But we will see how that changed when we started to analyze the real data. The other question at that moment that came up was, okay, let's move. This was more the question from the biometricians. Okay, so what should we use? What is the methodology? Should we use BLUE? Should we use Blob? How do we come up with it? So in that moment, again, we had some understanding. I remember Roberto giving a lot of feedback and insight on this part. We knew by default, okay, depending on the shrinkage, there's going to be differences, right? We're talking about shrinkage this morning, blues versus blobs. And actually that turned out to be true. What we observed first in the simulation, actually before having those conversations with the biometricians, was that when we were calculating the genetic gain with blues, we could see a realized genetic gain, and it was, let's say, closer to the true one than if we were using blobs. With blobs, basically there was an underestimation of realized genetic gain. So basically, if we were using blobs, we would say that we have a lower genetic gain than real. And we started to wonder why. So some of the things that came up was, well, this probably is because of the shrinkage. Because, what we are saying, and we were discussing that this morning, is that with the shrinkage, with the blob methodology, you have an intercept, but depending on the heritability, the entries will be shrunk or less or more. So if the heritability is really low, they get shrunken really, really hard. If the heritability is high, then they look almost like the blues. But again, the thing was that those estimates, if we say that this entry, entry 1 and entry 2, the performance is 11 tons, and the other entry is 11 tons 0.001, and the other entry is 11 tons 0.002, because the heritability is so low that basically there is a lot of shrinkage, that is not the actual performance of the entry. It's not the genetic potential. So it's good for selection. So, and I want to clarify this part. We're not saying for you to move to use blues. Use blobs when it comes to selection. But the point was that to be able to understand what was the genetic potential, that, well, how much we've been increasing the mean in the population, the blob methodology was giving us an underestimation that was more or less depending on how we were simulating the heritabilities. So it turned out that as we were simulating lower heritabilities, the underestimation was more, less, depending on these values. So at that point, after the conversations with the biometricians, we said, okay, well, then let's look at the methodologies that are currently used. And it turned out that the methodologies that McKay and Piepo were using in that moment, well, not some years before, for calculating realized genetic gain, they were actually considering the genotypes to be fixed. When I talked to Ian McKay about what is the reason why they picked, fixed effects instead of random effects to see if he would confirm, our finding, basically he said that they just felt that it was the right thing to do, but they actually didn't come up with a good explanation. And he was instead the other way around. He was happy to know that we were confirming his gut feeling. So I guess this is something interesting. Actually, several people have been suggesting that we make a publication out of this because it seems that we in the CG found some pretty interesting stuff. Okay, so that was the kind of how we got to the recommendation for calculating genetic gain, use BLUES. That was the recommendation at the moment. It doesn't mean that we are not going to make some improvements. For example, it has been suggested by the biometrics teams, okay, if the problem is the shrinkage, but we want to leverage from the connectivity between the different trials, and some of us have pedigree, some of us have relationship matrices, why don't we use a Blob method, and then after the analysis, we do regress. So basically, we remove the shrinkage, like, you shrink the material for a minute to use the connectivity, but then bringing it back. That has been used by some biometricians in the past. But again, that's something that we are going to explore this year. We're going to compare how good, how much the connectivity really helps in these cases when we use the Blob method with the pedigree or markers. So yeah, actually, sorry for going after. So basically, there's different types of relationships that can allow us to connect the data. Imagine for a minute, that this is your stage ones. Like Bo just said, I mean, you have different germplasm. It's not the same germplasm, the stage one from this year, from this year, from this year. The connectivity can be built by maybe putting some checks or some materials that maybe are present. Think, for example, on this material Z, and that is present in the 3 years, so that I can connect the data. But also there is some relationship that exists in the germplasm because they belong to the same founders. So this is the one that the biometrics teams want to leverage from, and this we just want to understand because we know that by default the Blob methodology will do that underestimation. So we just want to see how can we take the best of both worlds. Okay, so this is to be answered, like I said, depending on the heritability. If it's lower heritability, the genetic trend will be lower than expected or than the true one. All right, so that took us to a more technical question, which you wanted to know how the connectivity affects the actual analysis. And some of you might remember this example. So this is, for a minute, this is actually the analysis that we were performing. We were talking about a one-stage analysis. We actually ended up doing a two-stage analysis for simplicity, but just for a minute, think that the fixed part was the year effect or the non-genetic trends, the genotype effect or the genetic trend. Then the random part was basically the noise associated to the locations, to the years, to the experimental design. And then we had some residual, right? Something that we cannot really explain. And we were feeding at that level of environments. So the year by location combination. So this was the analysis, just for you to know. And then we wanted to understand the connectivity issue. So just think for a minute that instead of just this being a unique genotypes, that this is somehow a set of genotypes. So set of genotypes 2, set of genotypes 3, set of genotypes 4, and basically we are doing the analysis along 9 years. So across these 9 years, we have these different sets, and they never overlap. On the other hand, we could have an analysis where there is a set of genotypes that actually overlaps, across all the years, and still we have all the entries. So what we did is to just start first with this type of data set where there is no connectivity, and actually it's the exact same data set that we use for both. So what we simulated was a program that was making genetic gain, that was making progress. And you can see that in the first graph. So we were having a positive genetic gain for the entries, but we were also simulating that entry that is always present across all the years. You can see this. Of course, if it's the same entry, it's not changing its genetic value. It's the same genetic value every year. But for this particular analysis, we ignored this entry. So the only thing that we did is remove it from the dataset. This entry is not in that dataset. Then we simulated some error to show that, maybe the year effect was almost opposite. Basically, there was a big year effect in year 1, lower year effect in year 2, and lower and lower and lower, to the point that if you were only taking the phenotypes and you were plotting them, you would have no clue that there is genetic gain. So basically, this is kind of opposite between the genetics and the year effects. So basically, we had a strong year effect in early years and a small year effect in later years. And then we tried to calculate the genetic gain with the model that I mentioned, this one. And it turned out that we could not actually dissect, the year effect, and basically our genetic gain looked like 0. There is no genetic gain, but we know that there is genetic gain. So then we know, how important was this connectivity issue, right? Because when you have strong year effects, which is kind of the norm, it's usual that you have strong year effects, you needed this entry, or this type of entries, the ones that are present across all years. So basically, this type of individuals that are present across all years or across a big periods of time. So we did the exact same analysis. So this analysis, the only difference is having in the data set this entry or not having it. Nothing special about this entry. Don't think that is the best or the worst. No, it was just one more entry, but that we left to be present across all years. We have the same, the true value, the phenotypic value. We make the analysis, and then we can actually observe the realized genetic gain that is close to the true one. Like I said, ignore the intercept. The genetic gain is actually the slope. You can see that the year effect is plotted here, the non-genetic trend. And okay, that's how we figure out, okay, it's really important, the connectivity. Why? Because that individual, especially, if you think sometimes in terms of model matrices, in mixed models, etc., that individual becomes some sort of intercept, right? When you look at this figure, especially the biometricians, immediately will feel that this looks like the fixed effect matrix where you have the intercept. And that is that genotype. So it's like, even if you don't want to, by that genotype being present and not specifying anything special about the genotype, that will become some sort of intercept. So everyone will be adjusted with respect to that individual or that set of individuals. So then the question came like, does the type of connectivity influences the accuracy of this genetic gain estimate? Because here it looks nice. You have a genotype that is just present across all years. That's always totally, the perfect situation. But some of you expressed, I don't have that. I have some genotypes that are present for a couple of years, and then they disappear, and then a new one replaces its place, blah, 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 etc. And that was really good feedback. So we started to simulate different situations. So how to build a bridge? So we build a bridge, for example, as originally we said, genotype, one genotype basically present across all years. Then we simulate, okay, what if this genotype is present for 6 years? But in the 6th year, we're going to replace it, but they need to be together for 1 year, and then you phase that off, and then the next genotype keeps going. Or maybe, we don't do it for that many years. We actually do it for only 4 years, and then a new replacement comes. After 4 years, a new replacement comes. Okay, what if instead of 4 years, 3 years, a new replacement comes every 2 years to the maximum, which is, let's say, this genotype is replaced every 2 years. Basically, you just give time to test it once, and then a replacement comes, test it once, a replacement comes, almost immediately. Well, it turned out that it has an effect. You can see actually here the plot for the different scenarios. This was the control, basically when there is there is no check, so there is no connectivity. The previous scenario where we couldn't see any genetic gain, the accuracy was basically 0. So this plot at the bottom is the different scenarios that we have here. So you see here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, plus the control. So the control is not being plotted here, but there is no connectivity. And in the y-axis, you can see the accuracy between the true and the estimated genetic gain. So as we said, no connectivity, no accuracy. Depending on the type of connectivity, there is more accuracy. So it's better to have genotypes that extend for a long period of time as opposed to having them just for a couple of years, or the shorter the interval, the less the accuracy. But we also thought that it's not that bad, right? I mean, even if you have a very quick replacement of checks, even there, I mean, of course, there is some gain in accuracy, but we don't want to say something wrong. I mean, it's not that it's bad to actually have a quick replacement strategy. And just considering that, this is, of course, simple simulation, we can have more entries to build even more robust connectivity. This could actually be increased even for these, kind of aggressive patterns of check replacement. All right, so that's the first part of the story. So, that's when we came up with these guidelines together with the biometricians and say, okay, we can start analyzing it. Take your historical, trial data from your database, take any stage that you want because they will have the same slope that you will just change in intercept. Keep an eye on the connectivity. Use the blue method because otherwise there's going to be a lot of shrinkage. And thankfully, most of you just follow the recommendations and try to present the same standard method. And of course, there was always some changes, and that's what I'm going to discuss because some of your experimental design was more complex for some, and then you try differently. But then that's how we start the second part of the story, right? We analyze the data. The biometricians had their model ready to go. The data was at the end a bit more complex, right? We had more interactions, etc. We actually moved from the initial recommendation of making a one-stage analysis. We actually ended up saying, let's make things easier. Let's go for the two-stage analysis. And two-stage analysis when it comes to analyzing the multi-environmental, multi-year data. Three-stage analysis when it comes to really even calculating the genetic gain. So step one was to take one trial, so trial by trial, and remove the noise from the experimental design. Block, row, column, spatial kernels, all that part, to just get and extract the means of the genotypes. So you extracted the blues, in this case, on the two-stage analysis, you first extract the blues of the genotypes, and then in the second stage, you normally start to feed the rest of the terms, right? Year, location, interactions with genotype, etc., etc. So the two-stage analysis is normally proposed to kind of make the analysis easier because maybe this year you have an experimental design and next year you have a different experimental design and the following year a different experimental design, and it gets very difficult to fit a one-stage analysis because then the biometricians need to do a lot of tricks and create dummy variables and do some tricks to make it run. Instead, if you do this two-stage analysis, you first remove experimental design, and then this can be just fitted together. The difference was that instead of feeding the Blob model in this second stage, the recommendation that we came up with, it was being used. So you would extract actually the genotype, the blues, and of course from the first stage you also extract the covariance or let's say the standard error of those individuals, of the genotype means, and you use it as weights for the second stage. We can use different types of weights, but I'm just going to simplify it. And this was the part that it was different. Well, the part that was different first was to fit, like I said, the genotype as fixed effects in this second stage, which normally is not done for selection purposes. But the additional stage was to take those adjusted across environment, across location, across years, means from the genotypes, and do a regression with respect to their year of origin to see if there was a genetic gain or not. So then I'm gonna go step by step on what I think were the findings, but I'm gonna ask also, to Bert, to Johan, to Roberto to jump in if they remember something else that I'm missing. So I remember, for example, Bert and just combining stages, as we said, there must be no problem. Just combine the different stages, stage 1, stage 2, stage 3, because we thought, okay, initially we just said one stage might be enough, but then they came up with the idea that, okay, if the stage 3 was the stage 2 the previous year and was the stage 1 the previous year, these individuals are connecting the data sets as well. Let's put them. Yeah, sure. Sounds like a great idea. But then what we started to observe, was like a lot of dots over the plots. It was very difficult to see some real trends. Actually, Bert, I haven't been able to find your plots. I hope that for the next one you can share with me some of those. I'm sure that you shared it with me, but I just couldn't find them, so I tried to recreate in a very bad way what we found. But basically, maybe there was a trend behind, but the problem was that, stage 1 there is a lot of entries. Maybe stage 3 there's very few entries. And basically, maybe there was a lot of noise here in stage 1, and then in stage 3, maybe there was good data. There was just different numbers of data points depending on the year. And because the programs have not been completely steady, like it's not that the stage 1 is always 1,000 entries every year. For some of you, maybe 10 years ago, it was very few. 10 years later, maybe it's a lot. It turned out that there was just too many different numbers of entries. And there was too much variance, basically, across every year. So what came out from it is that, of course, there was a regression line. You can always feed a regression line. But the problem was that the dots that were surrounding the regression line, they were spread all over. And as I'm going to show in some pictures later, it turned out that the analysis that were using a single stage of data and that had good connectivity, those were the ones that actually gave the clearest trend. Of course, there was some uncertainty surrounding the genetic gain, but there was, clear connectivity. So, for example, and I'm going to combine, I guess, those two ideas between the connectivity of the stages, but also the coverage of the TPE. We didn't consider that covering the TPE was going to be as bad as it turned out to. It turned out that some of the analysis, actually, this is some of the WIT data that Kit analyzed. When they split the data by market segments, some market segments had several trials per year, 11 trials per year. Some other market segments only had 1 trial per year. And when we were doing the analysis for those different types of data sets with different levels of coverage of the TPE, this is a representative picture of what, there is many more examples, but believe me, this is a representative sample of how it looks like. The ones that had more trials, that they were actually in more locations and every year you have like a more robust coverage, they gave like clearer trends. So you can see here that, of course, there is always noise, surrounding the slope, but you can see a consistent, steady, increase. And it's not too much about the increase. It could be flat, but it will be consistent. If everything goes up, everything stays in the middle, or everything goes down. But when you are actually using data sets that have only, very few trials per year, you had something like first, you can see that there is very different levels of variance, like few variance here, lots of variance here, because basically there is a lot of the year effect is still there. And then suddenly, going down, going up, going down, going up. All these zigzag patterns. And it was very difficult to say, well, we have a trend, right? We can say, here is the genetic gain. And we said, okay, look, the genetic gain is 1%. But the problem was that, the regression line was not explaining the variability, and it didn't look, that robust. It would be very difficult to, take some strong decisions based on this type of zigzag patterns. But when there was, these more clear trends, even the R-squared, was higher. You could see that, of course, like I said, there's always noise associated, but you can see that there is some genetic gain that could be real there. Like I said here, the problem with this type of analysis, these are more pictures of that type of analysis where there is very few trials, you could see again that because there is these zigzag patterns, up and down. Just look at this first initial plot. It starts here, then suddenly goes up very abruptly, and then goes down abruptly, down, up, down. And of course, you feed a trend there. The problem with those type of analysis was if you remove 1 year of data, then it changes drastically the genetic gain. So suddenly, you had 1.85%. You remove 1 year of data, the first one, and it's 1%. You almost cut it in half, just by removing 1 year of data. And of course, that it's not that, at the end we know that you're going to be honest and say, well, we put all the data. But it can be very easy to manipulate basically these data sets. You just remove maybe the ones that, affect the trend, and 2% genetic gain. Yeah, Johan tried to do that several times, and nah, just kidding. No, he didn't. He was one of the ones telling me to that this was happening. No, just kidding.
If you don't know, they're really looking for the very big genetic gain.
Yeah, exactly. There it is. Yeah, remember there is recorded. Yeah.
I have a simple question here.
Yeah, sure, Bello, please go ahead.
Software is too low, but
Yes.
still the gain is more.
Yeah, exactly. That's what we're saying, right? Like this type of regressions is a lot of noise. The R-square is very low. Actually, the regression is not explaining anything. Yeah, so, and it's because, we have very low number of trials. This was not good quality data sets, but it was not fault of the program. It was just that for some regions, for some market segments, there was very few information. And for some market segment, there was a lot of information. Like for the one that I was showing here, this has much more information, right? Like I said, even though there is always, noise associated to the regression, you can see the difference even in R-square, right? We're trying to still, figure out what are the right measures of quality for the analysis. But if at the end of the day, what we were going to put in the report was this number, just the rate, and nobody had a clue what was behind, it can be very misleading. So that's one of the improvements that we need for this year. And the biometricians and EIB are working together to come up with what are those measures of quality? What do we put to make sure that when we look at these reports with these numbers, at least we know what type of data is behind. So yeah, the connectivity, it turned out that it was not as good as we expected. Actually, there is some nicer plots from BERT where you have huge correlation matrices. I still remember them. And what we noticed is that there was some data sets that were almost perfect. They had so many genotypes that were connecting the different years, but there was some others where there was just blocks, that there was no connectivity at all, that it was just like the program suddenly stops using completely the same checks and then just start with a new round of checks or new round of materials, like these ones where basically the connectivity is really low versus things like these, right? This is, let's say, an analysis where there was the entries, and then suddenly there was, these checks that were present across all years, all trials. Like, I'm not saying that this is necessarily the way to go, to always put the same for the next 100 years, not yet, but there was good connectivity patterns. And those are the ones that, like I said, were showing those clear trends. Why? Because like we said, the whole point of the connectivity is to remove the year effect as good as we can. And that was being achieved by some of those analyses. From across all the centers, we found, I'm just putting some examples, but we found good analysis and bad analysis across all the centers. And not analysis, I would say data sets, structural data sets. Something that actually some of the biometricians noticed and they shared with us is that also even the type of check or the type of material that was connecting the data sets had an influence in the rate of genetic gain. And that was actually, well, it's still being for me a bit concerning, right? This is actually something that makes the job even a bit more difficult because at this point we were like, okay, Then let's just make sure that we can connect the data sets. Let's put some entries that can be, spread across all these years. We can put some phased strategy, and that's it. But some of them actually suggested that even the type of entry that you decide to connect the data sets can have an influence. And they put some examples like this one, where they had this check, Mexicali, that in a particular year, it performed poorly. Like everyone was doing more or less the same. Also this Mexicali, and then suddenly, boom, that one drops down in this particular year. And then basically, we expect that there is going to have an effect under the null hypothesis, that there's going to be an effect in 2014. Under the alternative hypothesis, that is not going to have an effect. And suddenly, when you run the analysis without this particular check, so, all the controls versus omitting that particular check, then we see differences. And differences that are considerable when you look at the genetic gain. So we're talking about 0.77%, so close to 1%, versus 0.5%. So it's like a 50% decrease, 40% decrease based on, how the connectivity is being, is being built by these different checks or these different entries. Of course, it might be also related to not only this, but to the fact that this particular data set also had maybe some up and downs. I mean, maybe just when we put everything together, maybe the effect of the check will be less. But in general, that was observed. They had another example that they showed. Okay, we had these two entries that actually, they don't behave also that well, that they make a sudden drop in 2014. Sorry, and well, that seems to be also affecting. I think I maybe forgot to put something else, but yeah, the point is that it seems that the checks that are connecting have an influence in the final result. But of course, probably, the problem is that these are also real data sets, and there's nothing wrong, of course, with real data sets as well, but in the real data sets, we have more than one factor maybe failing, right? For example, you can see that maybe also the quality of this data set was not necessarily the best. So if he doesn't have really that many trials as well, then we put on top of the connectivity also the checks. I mean, there might be several things that were making this particular data set fail. So that's where the simulations can also help. So, but still something to be improved. But the current recommendation that came out after that analysis is to at least look for entries for connecting the data sets across years, entries that can be dynamically stable. So those genotypes that when the environment is good, they are good. When the environment is bad, they are bad. I mean, nothing that has a lot of G by E that basically is just jumping all around the place. No, we want entries that can follow the trends, the environmental trends, the year trends. And something from, I still remember this from Africa Rise, if I'm right, from Roberto, suddenly there was also, some connectivity there. But when you extracted the means for the entries, you would take what you expect, of course, is that the check, even though it's present across all years, it doesn't increase its performance, right? Because it's just the exact same genotype. Once you remove the year effect, you expect that genotype to be relatively stable. I mean, we know that nothing is perfect. It might be jumping, but when you fit a regression line, it should be a zero slope. Well, in some data sets, this is, I think, from Africa Rise, but they explained that this was really not the best data set, but there was certain level of connectivity there that we thought it was good. Well, when you were, for example, plotting this particular entry that was connecting across years, if you extract the mean of this individual for the different years, well, it turned out that this person, even after the adjustment, this entry was still increasing, which means that it was not really correcting properly. And actually, when you were looking at the genetic gain that they were reporting, it was just too high. But look, I mean, how much certainty you can have in when you have something like this in a given year, and then you say, I'm making 3.23% genetic gain, but you say that the check is also increasing 2.68% genetic gain. So those were nice findings, when the biometrician started to analyze the data sets. So like I said, if you want to jump in and say something, please just take the microphone, because I think you have some of the details there as well. But we started to identify there was issues, and mostly the issues were in the connectivity and TPE coverage. I'm going to stop there to have a break, but maybe before we have like 10 minutes questions before I keep moving. So any thoughts, comments, questions, and then we can go for a break. Are we? Yeah. 2:54. Do we have another presentation after myself? Yes, me. You still? Christian, but nobody wants to. No, just kidding. Then let me just go through the last 5 slides. We have a break of 5 minutes, and then we come back. Is that okay? Yeah, let's go for it. Yes, sorry. Someone told me that you were starting tomorrow or Thursday. Yeah, tomorrow we have the trip. Yeah, that's true. Yeah, don't worry, we're friends. So yeah, some last questions that I want to share with you. Well, more than questions, isn't some of you actually wanted to know how that looks in practice. So there were some questions. Sorry for jumping in. I just wanted to check. Some questions on how many checks should we plant. We still don't have the last answer to that question. When we were doing some simulations, it turned out that, of course, the more entries you put, the more robust, the more accurate it gets. From there, we also understood that it was not too much about the number of checks, but really about these steady entries. Actually, let me just skip this one and focus on this particular slide. So currently, the recommendation is that there needs to be maybe 3 or 4 entries connecting. And I know that this is where the controversy comes, because for some of you, 3 entries for connecting the trials that need to be present every year in all the trials that you will use for a generic game can be, maybe too much. But just to clarify, when we've been talking about these steady entries, we're not talking about, putting them as checks across all the trial, like to adjust spatially or something. No, it's just entries, additional entries. If you're just testing them in stage 1 in one single rep, well, put those entries with a single rep. If they are in the stage 2 with 2 reps, well, just put them as additional entries with 2 reps. Of course, we know that it gets still a burden when you get to the very late stages, when maybe something is very few entries, like 10 entries, and then you have to put 2 or 3 additional entries, then it's like, oh, well, this is still 20%, 30% more, entries than I was managing. That's the part where maybe we have, well, you need to have this conversation with the donors and with the leadership to understand, okay, what is the compromise? I mean, if we're going to do this, do we get more? Do we instead do it in earlier stages so we don't have to spend more money? I mean, what is the compromise? So those are the steady entries, 2, 3, 4 entries that can connect, and then you decide what is the replacement strategy. Because the replacement strategy, we don't have an answer actually for this one at all. We simulated it, we didn't find an answer. We tried to keep everything orthogonal, try to understand the treatments, but we couldn't figure out what is the good replacement strategy with simulation. Maybe we just need to go to the drawing table. We asked some of our collaborators from Bayer, Corteva, etc. They say that they are just doing it 1 per year. They also don't have a clue what is the best. They also did some simulations, but they also didn't get the right answer. So some said 1 per year, etc., etc. We think that this is pretty much an open area where you can just play with it. If you have to change it every year, change it every year. If you cannot change it every year, or you decide that you're going to keep some checks for 4 years before you phase it out, that's really okay. At least from our perspective at this point, we don't have a recommendation. So last comment, just to clarify. So how it looks in practice. We've been talking about check strategy, and also Christian is going to go a little bit on that part, and that's why I think it's a good final 2 slides. Because we talk about check strategy, and immediately I think what comes to your mind is, spatial adjustment, commercial checks, etc., etc. And if you think for a minute in, different years in your breeding program, in different locations, where you have planted different stages, let's say stage 1, stage 2, stage 3, in a given location, another location, another location in year 1, in year 2, in year 3, or just I plus X, I plus Y. When you talk about the spatial adjustment, where you're talking about those checks that need to be present in different areas of the field to make a proper adjustment so the means of the genotypes that you are actually considering entries for selection get properly adjusted. But when we're talking about the connectivity entries, we're talking something more like this. Notice that in the previous picture, the checks are different. I'm putting them by colors. Depending on the year, they might be different. Maybe some might be similar, some might not, and they are trying to cover the field. When we're talking about connectivity, we're just talking about keeping the same entries across years, not with a particular arrangement in the field, but just to be present. If in the early stages the entries are only present once, well, just put them once. If they are present twice, maybe in stage 2 you have 2 reps, okay, then put them twice. If you have in the next stage 3 reps, okay, put them 3 times. Just an additional entry there, an additional couple of entries to make the job. And so let's make the differentiation then between those spatial adjustment versus temporal adjustment. Spatial adjustment might be this type of thing. Temporal adjustment, removing the year effect, is having those connected or connectivity entries. And I know that you want to say something maybe about the commercial checks. Can I use my commercial check to be this one, or can I use that type of check to be this one? That is your decision. From our perspective, we just have 2 types of checks. The ones that you put there for some sort of a spatial adjustment, and that I'm also including, when you make your comparisons with the eye or with the data, what you're trying to do is some spatial adjustment, right? When you go to the field and you say, here's my commercial check in this part of the field, you just want to check, how it compares. In some sort of a spatial adjustment, whether it's based on eye or in an analysis, fancy analysis from the biometrics, that is a spatial adjustment. And the temporal adjustment is the one that I'm referring to. If you can use your commercial check for being one of these 2, yes, for sure. But you take the decision. You take the decision if your commercial check, it should be a check for a spatial adjustment for comparisons, or you also want it to be not only present for 1 year or 2 years, but you also want it to be present for a long period of time to also act as a temporal adjustment entry. Okay? And that's pretty much it. This is just about predicted genetic gain, but there's nothing there to be shared. So, some questions or comments? Because Brenda has the microphone there ready to address some of the needs. So we're working for new recommendations or improved recommendations, but is there any doubt up to here? I mean, I'm lucky that here we have all the team of biometricians as well in case I'm missing something. So this is the best time to ask. Mokhtar, yeah.
I woke up.
Oh, yeah, now you're going to say, oh, I don't understand that last slide.
Yeah, I mean, I was just wondering, because for potato right now, in the early generation trials, we do have not that many replications, maybe 1 row and maybe even 1 replication. So I was thinking maybe by doing sparse testing, maybe we would be able actually to have that information we need to estimate the genetic gain at some point.
Keep that question for exactly the next presentation, Mokhtar, because we're going to talk about the sparse testing stuff, adjustment. This is mostly about just trying to tell you that we need some temporal adjustment across years, and you need some entries there, but not necessarily trying to tell you like what is the best level of replication right now. That's kind of coming right after this one. So I'm not telling you, replicate 1, 2, or 3 times. That was just a Mickey Mouse example to show you that the type of connectivity entries that we're looking for. Okay. But yeah, so just keep that for the next one. Xiaofei?
So in your last 2 slides, you talk about the checks and also the connectivity varieties. So what will happen if we use the same? For example, if we use the stage K for genetic gain calculation.
Yep.
And we use the same 5 variety and checks for field the spatial adjustment and also for these connectivities. Is there any effect?
No, there's no problem with that from my perspective. Maybe I'm missing something, but please try to jump in. This could be easily also a spatial adjustment check. But like I said, the problem is that you just need to make sure that this individual then is going to be present next year, and 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 in this trial, that trial. So that's just, but we still can act as a spatial adjustment check. But you see my point? I mean, you're the one that decides what material goes there, and it can act as spatial, as temporal, as both, as commercial check. But you just have to come up with a strategy that ensures that we can monitor genetic gain. So maybe one of these entries might stay for several years, but some other entries might not stay. They really are purely spatially adjusted, entries for spatial adjustment. But some entries will have to stay even beyond that purpose. Because, I mean, in this case, I'm not worried about the shrinkage because that is not, like I said, we addressed that part. So even if this material is more replicated, let's say in this year, than in this year, than in that year, we don't expect that to have, well, it will have some effect, but we expect that it will not be necessarily negative, right? It will be a positive effect. If that particular entry was actually more replicated, that means that it can make a better adjustment for the year effect. Yep. All right. Oh, okay. Rosa and then Maria Fernanda.
So regarding this issue of the instability of some checks, we should be careful that we know that this connectivity check before we start using it as a connectivity check, make sure that it's a stable entry. Yes,
that's a good point. Yeah, it would be great that you know, when you are doing your regular multi-environmental trial analysis, some of the things that sometimes your biometricians provide is the performance versus the stability of the materials. So basically we're saying, okay, if you're gonna pick something to connect across years, it might be good that you look for an individual that has just good stability in the dynamic sense, but they always give you that one. The performance, we don't expect that, you know, it doesn't have to be the best entry. It can also be something average or something low. That really, mostly is just the fact that it will respond to the environment. So yeah, you can just take some of those most stable entries from the meta-analysis from your last selection, and that can become your steady entry, your genetic gain check, whatever name you want to put it to that entry. Maria Fernanda?
We have the issue of changes in the agronomical practices, and that could hide the genetic gain or help make us believe that we have a really huge genetic gain instead of.
Yes.
Is there a way to, because we are advancing all the time in agronomy, we have to change plenty of managements, and that's becoming also an issue.
Yes, no, that for sure, that's built in the analysis, right? Well, in essence, what we are fitting is not only the genetic trend, but also the non-genetic trend. So basically all the changes that have been happening in the agronomic practices. So normally that's captured by the year effect and all the other terms that, you know, location, trials, because those are kind of capturing those differences that have been happening. And that's why, you know, normally when you see those genetic gain analysis papers, they normally plot both the trend and non-genetic, the genetic and non-genetic trend. But that is captured by this analysis. Like I said, depending on how robust is the data set, that might be captured better or worse. But yeah, that is captured, no problem. I would say that if you have any other question, let's, can we take it maybe? It's just that I just noticed that, yeah, I stole a lot of time from Chris' presentation. I took already like 15 minutes from his time. So let's just go for 5 minutes break. Then we come back. So 3:15, we come back and we start with the med part. And yes, we can just discuss it outside. Thank you.